Hello and welcome back to the lab. Today on the bench is my SICK SG504. This is the high frequency signal generator from Tektronix. It's a TM500 plug-in. I was starting to work on my 7904A, recording a video for that, and going through the necessary calibration equipment, I found I needed this unit. So I have to repair this unit. I know there's a fault on this one. Everything works, or it works for the most part. There's a fault on the high range. The low range and the reference work fine, but the high range is dead. It doesn't output anything. Well, it doesn't level. So we're going to do some quick testing, dive into a schematic, take a look at this, see if we can't get this thing healthy again. One thing to note about these is if you're going to try to source one of these from the secondary market, almost every single one of these that I've seen, it does not have the leveling head. This unit will not work without the leveling head. Doesn't work. Absolutely must have the leveling head. You can get RF out of the port, but it won't be leveled, so it won't be a leveled sine wave generator. So I don't know why people don't list them with the required leveling head, but there is I will leave it in a link in the description down below. There is a gentleman on eBay that is making leveling heads. I actually have one of his, and it actually works quite well. It improves the specs a little bit over the Tech leveling head. There is a leveling head option available out there, but you do need it. I haven't been able to repair this in the past because I haven't had actually scopes that were fast enough to look at the signals that I needed to come out of this thing. This generator goes from about 250 megahertz right at the top end of the SG503, but then it goes up to 1.06 gigahertz in terms of sine waves. So I haven't had anything in the lab that was able to handle anything this fast before. So now that I have the DSA, we can take a look at some of the signals out of here. We can see if we can get this thing repaired. So I have it set up on the low range now, about 330 megahertz. So all the way down on the amplitude. And we will turn the generator on. And we get some triggering, and there we go. The noise you saw in the trace here was just the DSA building the waveform and doing the sampling. So that is expected behavior. 327 megahertz, and we have half a volt peak to peak, which is exactly what I have it set to on the front end. So low range works. See what happens when we kick it into the high range. This should read about 600. It's building something. And here we are in the high mode. So you'll notice a drastic change in the vertical sensitivity. I had to go down to 10 millivolts per division. We're at 24 millivolts peak to peak as opposed to 500 millivolts peak to peak. So I have a sneaking suspicion we're just not getting. So the good news is here, the oscillator is running because my frequency is correct. We're right at about 600 megahertz. This is saying right at 600 megahertz, so the oscillator agrees with the front panel. So that gives us a clue, lets me know the resonant cavity is working, everything in the back of the cavity is working. I'm just not getting the drive level that I need because it's so low. Also, I'm turning up the front panel amplitude right now, and the signal's not changing. So I'm not getting enough drive out for the leveling head to do anything. So this leads me to believe that we have a mostly functioning unit, albeit with some drive problems. Let me pull up a schematic, and we'll take a look at some points of interest. All right, so let's see. Here's the main oscillator cavity for the high and low range settings. And this is controlled by the frequency knob. That goes into, so the low setting comes out and comes over here to Q120 and then goes into a matching network and then out the drives for the output. On the high side, which is where we're having a problem, comes into Q70, same matching network, but then this comes over and then goes out our high side over here. So we have a Q120 into an impedance matching network for the output, and then we have Q70 into an impedance matching network for the output. So we have a very convenient test point after looking at this, which is right here, which is post the impedance matching networks. This is the frequency monitor out on the SG504. So if I'm getting enough drive, because this comes in from control and bias supplies, the output of Q70 should show up on the collector up here, and the output of Q120 should show up on the collector up here. So if everything is working correctly, I should get a decent amount of drive signal here. If I'm not getting a decent amount of drive signal here, because we know the oscillator's running, that's pretty much pointing the finger at Q70, which is where my problem's going to be. These are all ceramic capacitors and inductors, so there's very little that could go wrong in here. At least at this point. These aren't like electrolytics or tantalums or anything like that. These are surface mount ceramic. Not saying it's impossible. Very unlikely. So I'm kind of zeroing in on Q70. I'm going to set up the DSA again, and we'll do some testing at the frequency output and see what we get. Should be telling as to if we're getting enough drive. If we're not getting enough drive out of Q70, I'm going to test this transistor, but I'm also going to look at voltage supplies, because if I'm not getting, like if one of these diodes is kind of messed up, and I'm not getting, if one of these diodes is opened or high resistance, and I'm not getting enough voltage through to the collector, it won't be able to swing enough to generate the signal that I need. Now this Q70 and Q120, these are both some very high frequency transistors, so if one of these is bad, I mean, I'm sure I'll be able to find a replacement, but these are going to be on the somewhat expensive side. Probably talking tens to 20s of dollars per each. So not horrible, but my gut's telling me that Q70 is going to be my problem. But further testing will prove that out. Okay, I've got some drive. I've got unleveled drive hooked up, so the leveling circuit's not running at the moment, and I've got it into a 2x attenuator because it's a little hot for the 11A72. But at 1 volt per division, I'm getting about 2.6 volts of signal output just to the cable that's the input to the leveling head. If I switch it, and this is at the low frequencies, 330 megahertz, which is fine. If I hit it to high, and we back this down a bit, I'm still getting drive out, but I'm not getting anywhere near the 2 volts output to go to the leveling head. It's 1.38. So that's starting to confirm suspicions. Let me move this over to the frequency. I'll set this to low. Take the attenuator off. Now this is the frequency monitoring output. So so we're getting about 800 millivolts of drive signal at the frequency monitoring output. If I kick it to high, collapses. It's there, however, it's not right. So, do we have a voltage problem or do we have a bad transistor? We will check both. Okay, here's our RF board opened up. This is on the right side of the unit. Here's our two transistors of interest, this guy and this guy. I'm gonna check this tantalum cap too, because there is a tantalum under here. This might be a problem if he's shorted. The transistor's not gonna get any drive. That would actually be really nice if this tant was the problem. But let me get the meter warmed up and we'll do some measurements. Okay, I've been working on doing some measurements, and I have, if I go in here and I measure to the connector, I have a dead short across this connector. So let's keep chasing it backwards and open up this resonator cavity, see what's shorted out in there. Okay, I should be reading a short coming into here, so that's kind of what's attenuating that resonator cavity. So that is correct. What I'm seeing on the cable is correct for the way that's wired. So let's dive back down to the underside and see if we can't make sense of what's going on with that transistor. Okay, well, we're making progress. Turns out it's not any of the RF components. I was looking at the transistor tested okay, Q70 was alright. Thought there were some weird grounding issues. They turned out to be okay. But if you look, we're at 600 megahertz. Actually, let me turn off the touch panel so I can touch the screen. We're at 600 megahertz, and I have a decent signal. Also, the unleveled light is off. So I was messing around with it, and given that the RF parts were testing okay, that led me into the buffer section, possibly testing the buffer amplifier. And I moved it back and forth a few times because I plan on doing a whole calibration on this unit. Anyway, and in moving the buffer drive current control, the signal popped out and the unleveled light went off and everything started working. Now you can tell it's kind of collapsing and moving. Something's still not quite right, but for sure now we have it's collapsing right now on camera. Unleveled light's lit again, and I'll show you guys what will happen here in a second. So for sure we have a buffer drive current problem, but I can bring this back just by fidgeting with that control. So I'm going to look into the schematic some more, take a look at the buffer drive amplifier section, and specifically where that control is playing around. We're also going to recap this unit because it's got some capacitors in there that I'm not 100% sure of. So those are coming out. We may have some power supply problems as well. But let me show you what's going on. Okay, we're on the high range, and the unleveled light is lit. All I'm going to do is I just moved the control as you saw, and the unleveled light goes out and comes back. So I think that pot may actually be bad. While I'm doing the capacitors, we're gonna replace that potentiometer as well. And if I move you guys back to the scope, the signal's back. So making progress. Okay, moment of truth. I have the new capacitors in. I have it's set to high range. I have the new potentiometers in. Leveled light, unleveled light is not lit, and I have a waveform on the scope. So cautiously optimistic at this point that we may have solved the problems. I'm going to let this burn in for a while, just let it sit in the lab and crank through. I don't want to leave the DSA on and just burn up that much power while I'm just letting this cook. So what I'm going to do is I'll set it about 1 volt peak to peak, and I'll throw it up on the spectrum analyzer and just let it sit on the bench and let it just cook for a while. Make sure the waveform doesn't collapse. We don't lose. It doesn't start acting squirrely again. Given that we replaced capacitors in the power supply and we replaced some of the controls Actually, here were the potentiometers that were replaced. These guys, they were 500 ohm pots. I had some 500 ohms, half-watt pots here from Bourne's, and actually, this right here is exactly what I replaced them with. So, for those playing along at home, I do need to get these to work, you do need to bend a pin, because these have the tri-pin. Come on, focus. The tri-pin configuration, as opposed to the all in a line. But they fit in just fine, and everything is good. So no magic smoke yet. I'm going to let this burn for a couple of hours, just let the pots bed in, make sure we don't have any other problems with it, make sure the leveling head doesn't go stupid, and then it will be into a calibration. And just for grins, here's the test setup. We have carrier at 602, so it's a little off by frequency. We can probably fine-tune that a bit. So, but yeah, I'm just going to let it sit and bake for a while, and we will go from there. Not having to deal with that RF transistor is fantastic. So I was not looking forward to trying to source that if that ended up being what was bad. I would have never guessed that one of the pots was toast. So, but cautiously optimistic, and time will tell. Okay, I've had the lab warming up for a while. Everything is good. I've got the 7510s warmed up, past its hour-and-a-half time. Let's see, I've got the 6500 on just in case I need it. My spectrum analyzer's on, been warming up. I know I'm going to need that. My frequency counter's on and warming up. I know I'm going to need that. But I think that's about all we're going to need for this one. I don't have some of the calibration equipment that this procedure requires, but I do have other, I have more modern gear that's better spec'd, so we will be able to get this into specification. But I will not be using exactly the calibration gear that tech calls for, but that shouldn't matter. So, as with everything, we start with power rails. I have to adjust the 18-volt supply and then check the negative 18-volt supply and then check the 5-volt supply. So let me get that hooked up and we'll get started. Okay, we're a bit hot on voltage, so I'm going to bump this down just a bit. I like the way this control's done. It's a very stiff control, but I have good adjustment. Well, that's about as close as we're going to get it. I'm allowed 20 millivolts, and I'm out by 2. Okay, I have to move the control. This was the control that I was adjusting, hiding back here. And we got to test the 5-volt supply, and I have a tolerance of 300 millivolts on that. The 5-volt supply test point is down here. Right there. No, it's not. That's test point 2. The 5-volt supply test point is right here. And we're allowed 300 millivolts. We're at 4.98, so the 5-volt rail is perfect. In step 3, we need test point 2, which is where we just were, over here. And we need to hit the low range. And we should have a meter reading of negative 14 volts with plus or minus 400 millivolts. Negative 14 volts, well within spec. Now it wants us to add a 10x attenuator here, which I've done. This is the leveling head, so off the cable coming from the unit to the leveling head, drop it by 10x. Now it's saying we should get approximately 22 to 23.2 volts. I'm a little light there, but it says to record a value that is 1 volt lower than the actual reading, because we'll be needing that in part 8 and 9. So 18.89. Okay, turns out I don't have a 330 ohm resistor that is that large, or that's a 1 watt. I have some 330s, but they're not 1 watt. So I'm going to be using my electronic load in constant current or constant resistance mode. However, the polarity here is reversed. That's important, so I don't damage the load. The load needs to see a positive voltage because its outputs are floating. I can do this. It needs to see a positive voltage. This is not. I'm working with negative voltages, so the leads are reversed. So even though I'm working with negative voltages in the SG504, I'm dealing with positive voltages at the DC load. So if there's any questions on how to hook this up, don't do it. This could potentially damage things, especially if you feed a negative voltage into the DC load. The pass elements in the DC load are not going to like that. So this has to be hooked up in the correct polarity, which is not intuitive for what needs to happen, but it's letting me proceed with the calibration. That's why it looks kind of funny. 5.5, that's exactly what we're expecting. So that is working as normal, and I'm unleveled, which is correct. Record a value that is 0.4 lower than the actual reading. Record this value we use in step 6, part 8. All right, so 5.5 minus 0.4, which would be 5.182. Okay, test E is test point right up here with the ground, and I'm looking for a negative 12 to negative 12.9 voltage on the meter. We have negative 12.5, so our buffer bias voltage is perfect and right in the middle. So next we need to check the output of the 0.05 megahertz and the 6 megahertz references. I'm checking the 50 kilohertz, and our harmonic distortion at 5.5 volts peak to peak is 0.5% total harmonic distortion. I need to, it looked okay on the scope. The spectrum analyzer confirms it. At the low end, wind this back down. 0.8, so we are good there. I need to step it up to the 6 megahertz. Take a look at that. And then we'll be on to step 7. Okay, we're doing the RMS amplitude settings for the 0.5 and 5.0 settings. So my target, because the meter is working in RMS, not peak to peak, I also have the 1 mega ohm impedance set up. So we have a 1 mega ohm resistor into a BNC to banana jack 50 ohm load leveling head is how it's set up to give the meter a 1 mega ohm input impedance. But I need this to be 1.17675. Well, that's about as good as I'm going to get it. Now what we need to do is we need to wind this up to 5 volts. And then I want 1.7675. Same thing. That's about as close as I'm going to get to that. Let's go back down to 0.5. I am barely putting pressure on this control. It is not taking a lot to get this adjustment done. It's probably about as good as I'm going to get that with that potentiometer. This needs to come down just a little bit. These two controls interact with each other, so you have to do this a few times. Well, that's about as good as I'm going to get it. There we go. All right. And we were able to do that with the meter because this was set at 50 kilohertz, which is well inside the AC bandwidth of the 7510 or the 6510 or the 6500. Both of them have the same AC spec. Just I get an extra digit on the 7510. Okay, I have the leveling head set into the spectrum analyzer. We have a reference level of 21 dBm, and I'm using some different settings because this is a fast enough spectrum analyzer I can get a decent display. But it's a center frequency of 405 megahertz, start frequency of 210, and a stop frequency of 600. And I'm using a bandwidth of 30 kilohertz. We can speed this up a little bit if we do bandwidth, resolution bandwidth, 50 kilohertz. That just does 30. 100 kilohertz. And looks good, but our noise floor is a little higher, which is totally fine. And everything is good there. It tells you to set up the spectrum analyzer. You don't do anything with it in this step, which is bizarre, but that's what they wanted you to do. The important parts of this step are on the voltmeter. So we have ground on the ground test point, and then the buffer current test point for a reading of negative 15.9. We have our reading of 15.9, and now we have to move the positive lead to test point 2. And we need to check capacitor C125, and we're looking for a balance. It has, as I have to wind the frequency up all the way to the top of the scale. We're at the bottom. And what I'm looking for is this to stay above negative 14 volts, but below 18.89. So if this goes above 18.89, I'll have to adjust C125. If it goes below 14, I'll have to adjust C125, and we'll go from there. So I have to wind up the frequency slowly. Okay, so you guys can see what's going on. Here's our frequency, and we're going to start going up. We're just going to watch it on the meter. I'm also watching on the spectrum analyzer to make sure it doesn't crash out. It's okay, because I'm still at 14.9. I'm just not allowed to go below 14. So if this hits 13, I'm going to have to adjust that cap a little bit. We're a little too high, so we need to adjust. Okay, I was getting some funny readings on the setup, so I tested step 3 again, and now I'm getting 22.5, which is more than I should have, so that cap needed to be moved, needed to be exercised a little bit. So this needs to be updated to 21.54. Let's check our oscillator again. This should now level correctly. And we're here. Low band, right? Yeah, low band. 21.49, 21.54. So that is exactly what we're supposed to have. Just to be sure, since I adjusted it, I'm going to wind it back down, make sure we don't go below 14, and then I'll be back. That's kind of nerve-wracking when you're doing it and watching that bounce all over the place. I reset the statistics buffer as I was before I had started, and you can see our maximum was 14.83, minimum is 21.63, so that is absolutely perfect in what we're looking for. So that one is correct. We need to check the high side. So I'm going to wind it back up to the high side, and then I need to do the same thing. And then we'll need to play with the spectrum analyzer a little bit. Okay, for this one, the digital multimeter goes across our 615 again, so a little bit ahead of myself checking the high range, but it goes across our 615. I have to wind it down the scale, and I need a half a volt below 5.182 for this to be in spec. All right, again, using the meter to my advantage and doing some statistics, we have maximum of 4.8 and a minimum of 3.09, so we are good. Okay, I have to wind through the frequency again and just check the harmonic suppression, and I'm looking for delta markers. I need the main delta marker to be 27 dB down, and I need the third harmonic to be 42 dB down. So this needs to stay 27, that needs to stay 42, and I just got to run through the range again. Okay, everything is fine with the harmonics. I set the line here at the highest harmonics I saw, which was right around, I think it was like 31 dB. So that's fine. I got to get set up for the high range. We'll do it all over again. Okay, and our high buffer is a little off, so let me do this adjustment real quick. The high buffer, high current buffer is here, and that will need to be adjusted. It helps when you're on the right resistor. The high buffer current still needs to be adjusted. However, the low buffer is here. The high buffer is the resistor right below it. You want to be on the top side towards the top of the board. I was on the low resistor. I'm now on the high resistor. I was wondering why the adjustment wasn't doing anything. Okay, more of the same. I have to watch the spectrum analyzer while I turn the knob, make sure the unleveled light doesn't come on. And if it does, I have to adjust C75, which I'll have to take it apart for. If I don't, I'll have to, if it doesn't, it looks good. So Let's take a look. Nope. We're going to have to do the adjustments, so let me get the RF cover off. Well, our 56 ohm resistors came in, so this is what I ended up picking up. These are half watt instead of eighth watt. They do fit, barely, but see if I lost that or if it has become carbon on the bench. Looks like it may have become carbon on the bench. I'll need this for later. I was having some leveling problems with the SG504, and what ended up happening is some very odd faults. It would work, it wouldn't work. I pulled the capacitor all the way out, and it was kind of working. It was trying to work. It wanted to work. The unleveled light would get dim, flash, come on. It was acting very strange. So I did a whole bunch of tests. Now the original leveling head that came with the SG504, it had a fixed cable on it. It didn't use an intermediate coax cable. And I was only having leveling problems over a gigahertz. So right at about 1010 to about 1040, I was having leveling problems. So I got the precision coax cable that I have for the SG503, which is a very tightly toleranced and spec'd 50 ohm cable. And all my problems went away. So it's a matched length to this cord. So my leveling issues went away. It now levels completely up and down the spectrum, and everything's working. So I was having at right around the gigahertz frequency space, I was having impedance matching problems with the cable, which was causing a lot of my headache and frustration. So I'm gonna look for another one of these cables. Hopefully I can pull one into the lab, and then I'm going to dedicate this to this head, so the head and the cable will never separate again, and that'll let me use the leveled sine wave generator all the way up. I will also see if I can find one of the tech leveling heads for this and actually have the official Tektronix head, but at the time I picked up the other leveling head, those were not available. That's where we're at the moment. I'm waiting for some gear to warm up. Oh, it looks like the spectrum analyzer's ready. I had to warm up the 8596 due to the fact that 4411B, I need to look at some harmonics about in the 3 gigahertz range, so couldn't do it with that. So I had to go one model back, but my 8596 goes up to 12 gig, so we are good there. I will get everything hooked up, and we will take a look at the harmonic suppression for the 0.5 volt and 1 volt range. Sorry about the strobing screen. This is a rolling shutter on the camera and a CRT. So we have the signal coming in here. This big white chunky thing on the front of the spectrum analyzer is a DC blocking capacitor. This is a DC blocking capacitor rated up to 18 gigahertz. So plenty for what we're trying to do. Not that I need it for this, but one of the things that's different between this and my other spectrum analyzer, for those that are new to spectrum analyzers, is as you go up in frequency, the inputs get less tolerant of DC. My 4411B is, you can put 100 volts DC on the input and it's not going to hurt it. You can't put any DC on the input for this guy or you'll fry the input. But I've noticed that it's not that the 4411B is newer, it's just it only goes up to 1.5 gig. This goes to 12.8. So the same thing is true in the E series of spectrum analyzers is with the inputs. The faster the spec an goes, the less tolerant of DC it is on the front end. Just something to be aware of. Spectrum analyzer inputs are very expensive. Okay, I have the SG504 4 set to 0.5 volts peak to peak, and a 0 dBm for the reference level on the spectrum analyzer. So I need to just roll through the frequency band, and just look at the harmonic suppression for 0.5 volt and 1 volt on high and low. So I will do that. What I'm going to do is I'm going to do 0.5. Then I'm going to do, I'll come back and I'll say I'm at 1 volt, but during post we will speed this up because I just have to turn it real slow. So you guys will see it a lot faster than I do, and we're just looking to make sure that the second and third harmonic, which are here, so this would be second harmonic. Oop. What did I do? Oh yeah, reference level 0 dBm. Bump the wheel. So we have second harmonic and third harmonic. And I'm not going to get close to that because I'm playing around in here. That's probably my Wi-Fi coupling in through here at 2.4 gigahertz because my stop frequency is at 3.5, I think. So this spectrum analyzer is fully capable of seeing Wi-Fi. So there might be some Wi-Fi noise in there. Okay, I'm at the beginning of the low side. So at 0.5, and we're just going to go slow and see what happens. Okay, that looked pretty good. So I'm going to go backwards on the high side. And the high side looked good as well. So now we need to set the reference level to 20 dBm. Now I need to go up to a volt. Okay, at 1 volt, rolling up, and then on the low range and rolling down on the high range. And down on the, actually that was the high range, so down on the low range. And that looks good. So now we got to set some frequency accuracy. Let me get some stuff moved around, and we'll be back. Okay, I'm going to deviate from the Cal document by a fair bit. The Cal document wants you to check the frequency accuracy with the spectrum analyzer in a 7K frame. I have a very nice frequency counter that is amazing at what it does. Nope. 50 ohm, that's what I want. Make the input 50 ohm. So I'm just going to use the frequency counter to do the adjustments, and then the harmonic suppression of the reference, I'm going to do a THD measurement with the spectrum analyzer and make sure it's good. So I will be deviating from the Cal process quite a bit for the next couple of steps, but it's just because I have gear that can fill the role, and I actually don't have the tech spectrum analyzer that they want me to use. So I got to use the gear I got. The coil that I will be adjusting for the 6 megahertz frequency is right here. But the answer is we want it as close to 6 megahertz as possible. So, because it's a coil, we want to use a completely non-conductive tuning tool. Too big. There we go. This is a very, very touchy adjustment. Gonna be good with that. Now we need to check the 50 kilohertz. And my specification is, I need to come down a bit on the coil still. Slightly out of spec, just a touch. Let's see what that did. Yeah, I'm good. All right. Since that really didn't change anything, we'll tune this back up a little bit. It's about as good as I'm going to get it. Okay, harmonic suppression of the reference. So we're going to move over to the E4411 and do a distortion test. Well, that looks absolutely awful. System measurements, harmonic distortion. That's better. I want to get some more data points. Amplitude. No, wait. Span. Frequency. Yeah, center 6 megahertz. Let's see. Measure THD. .05% THD. So now we'll set this at 0.5 volts. So now we're looking at the THD at 0.5. Let's see. Stop the measurement. We do still have carrier, but it's lower, which is expected. So what if we turned down the reference level a little bit? We still have good harmonic suppression. Okay, checking on the total harmonic distortion of the 50 kilohertz carrier. We are at 0.018, so no problems there. Everything looks good. For the frequency accuracy, I'm going to go back to the frequency counter. Okay, I'm going to have to do the mechanical alignment, so I have to loosen these two screws down here. We'll have to get in there with an Allen key, pop those loose. Then I have to rotate this control to get it into mechanical alignment. Then we'll have to do electrical alignment, and we'll have to go from there. But it is out of alignment, and the frequency is probably the critical aspect of this unit. So we're going to get it into alignment. So I'm going to get that loosened, and I'm going to get that done, and then we'll come back. This is going to be very fiddly. This is going to be not easy to do, but we'll get it done. Okay, well, we hit 450, so that's back on 450. I can move it a little bit up or down, a little bit up, and we are tracking. That is right on the line at 450, so we're off by 16 hertz at 450 megahertz, so not bad. We are going to have to adjust the low range and high range, but we now have mechanical alignment. To be honest, that wasn't half bad. You just twist here and then tighten down the screw up here when it's lined up, and it's fiddly, but it's not awful. Good news in checking our 550. We are good because I'm allowed 2.75 megahertz at 550, and I'm only 1.37 out, so don't need to adjust anything there. Let's check the low range at 250. Here's our 250 megahertz, so that's in spec as well. I'm allowed 1.25, and that's 0.5, so perfect. Let's check the high range. Well, that's supposed to be 750, so that is not. Ugh. This one's not going to be nice. Okay, so what I'm going to have to do is I'm going to have to loosen the shaft, set it, loosen the shaft, then align the dial with the shaft is how I'm going to have to do that. So what I need to do is I have to set that to 750. I'll try to show this on camera. Set this to 750, which is here. So now what I have to do is I have to make this match this. Okay, these tweezers are coming to the rescue. These are, what are these? CHP 3SAs. They can get in there and they can actually hold that shaft while I'm adjusting it. There's our 750 megahertz. Now I have to line up the front end. Here's the fun part. This is how fiddly this is. I want to get this more accurate, so what I'm going to do is I'm going to adjust it with the coarse knob, and then there we go. I am off by 100 kilohertz on 750 megahertz. So that was fiddly, but we're there. Now I need to check the high range alignment. So 500 megahertz, here we go. Well, 500.36 is not too bad, and I'm allowed 2.5 megahertz. So 300 kilohertz, well within spec. All right, 1050. Oh no. Wait a second. No, it's okay. It got real loose for a second. I thought the shaft slipped again. Ooh. That did, though. Shit. All right, got to line that up again. Okay, we're slightly out at the top end, so that actually does need some adjustment. So let me get that adjustment out real quick. Take a look at that. I was using way too small a wrench. A lot bigger than I thought. Wrench I needed was a lot bigger than I expected. I'm going to have to crank that up a lot. Here's the coupler, or the oscillating assembly that I had to take apart. This coupler decided to crack on me and was slipping on the shaft. So obviously that's going to be no good. So I have to go through the whole alignment again because this is going to be real offensive to the calibration. Tearing it apart this far. These are the two oscillator sections. This is the low side. This is the high side. So I think the best way to attack this is going to be to pull the high side off, pop the, see if I can replace that coupler with something, and then go from there. So, it never ends. Okay, well, there's a weak point in these, and I ran into it, unfortunately, with mine. This is a nylon coupler, and it is pushing 60 years old on this unit. And the nylon's giving up, it's cracking. So the problem is these screws tension the shaft for the high section. And so I was like, okay, well, I'll get another coupler. Shouldn't be too much of a problem. Problem is it's threaded going into this side. So it threads in here, screws to the shaft over here, and it's a very unique nylon part. So what I've done is I super glued it last night to fix the one crack that happened, but I got everything back together and it cracked again today. So what I've done is I put a piece of heat shrink tubing over it, and it's holding. It's actually tight enough where the shaft is tracking, everything is good. To give it a little more insurance, we have a calibrated bread tie. It's a steel wire lined with paper. Everybody's probably seen them on bread. But it's wrapped around, spun tight with a pair of pliers, and snipped off. It's out of the way, it's there, it's holding, and it's tracking, so hopefully it'll get me through the next scope calibrations. Really, I need the low side, but I wanted the high side working. So Not the most elegant of repairs, but at least for right now, it seems to be working. I want to do some experiments to see if a signal generator could be used. I ran across a fluke paper that said an RF signal generator can be used to check the bandwidth and leveling of scopes as long as the accuracy was there. So I'm not doing anything. I'm only doing stuff up to about 500 megahertz. Not really pushing the lab much past that, at least right now. Who knows what the future holds. However, this does look like it's good to go. So let me set up for the last step of the calibration, which is checking the flatness regulation. Hopefully this stays in and we can call this one, we can toss this one in the rack. If that cracks again and it stops, the high side stops working, I'll just take that coupler out and disconnect it completely and then just use the low side, because I can still use it on the low end. Yeah, this has been one crazy calibration. So I'll have to get us back up to this step, but I'll do that tomorrow, and then we will check flatness. Okay, I've got us caught back up to where we were with the calibration, and I'm back with the peak-to-peak detector. We're gonna see how this works. The peak-to-peak detector is hiding under here. The main reason for it hiding under here is because I don't have a power supply. Right, I don't have batteries in it. The batteries are toast. These are what go in it. I need to order some. They're not cheap batteries, and they're only good for a year because they have a constant drain on them. However, I have the 2281 and I have the 2450. So we have the source measure unit and the Keithley power supply. Both are set up for 1.5 volts, which is what the batteries are nominally, and we will get power that way. Let me get set up for the flatness check. Okay, I needed 2.4 meg ohms across the meter impedance, so I have a 2.2 meg in series with two 100Ks soldered together for best connection, and we're in the adapter, so this will go into the 7510. Okay, our zero reference level at 50 kilohertz is 300 microvolts, so we will reset some statistics, clear the buffer. All right, we're going to check the 6 megahertz reference. We're there. Just change ranges. And that meets spec because it wants less than 1 millivolt deviation. So we're good, but barely. Now we hit low range. And all I need to do right now is just note the reading. Okay, I don't have a power meter, so I'm just going to do this direct on the meter. So what I'm going to do is I'll clear the buffer, and then I'll slowly rotate it up. And then we'll be back to take the... we need to look at the minimum and maximum and the swing. Okay, well, that didn't work the way I expected it to. Turns out my peak-to-peak detector is going to need some adjustment, so I'm going to need to figure out what that is. So I'm going to have to trust the leveling head at the moment. The good news is I've been fighting with this for a couple of hours now, and I'm getting numbers that are out of spec, but they're consistently out of spec and very close to each other. No matter how I set it up, how many times I dial something, the SG504 is being very, very consistent, but it's telling me that the I need a peak-to-peak amplitude of about 0.1%, and I'm getting 0.2, but I'm getting a consistent 0.2. So I think the problem lies in my peak-to-peak detector. So I'm gonna get some batteries for that, and I will readdress that. There's two adjustments in here to, I don't want to say level it, but bring it into alignment. I think one of those potentiometers may be out, so I do not know. Soldering iron's beeping at me, so I'll get these power supplies disconnected. This did not work as I expected, but that also means that the SG504 is as verified as I can make it, and I do not get an unleveled light all the way through the bands. So pretty sure it's working. I'm going to double check the low end range on my DSA because I'm well within the 1 gigahertz measurement capabilities. But so I'll run through that. But if that checks out, the low range is at least good. I can work on that 7904 frame and get that up and running because I need to get that 500 megahertz frame up and going. But so I think we're good. But I'd like to fully test it, but the lab's fighting me, and this thing has been this one's been a bear. So let me get that set up, and I'll do a final verification on the low range, and I'll do the high range once I get the peak-to-peak detector sorted. Well, I had a pleasant surprise when I dug into a spec sheet. Turns out the 11A72 on the DSA actually has a 0.6% accuracy. So well within spec to check the leveling, and the frequency ranges in spec to check the leveling at least up to 500 megahertz. Can't go to a gig because you'll hit the 3 dB roll-off, but for the low range, which is what I need for the scope, I was able to check it. And it does make spec. So I checked every 10 megahertz, and the specification on the SG502 is 4% of set point at 50 kilohertz. So wherever you set the amplitude at 50 kilohertz, 4% deviation from that. I had it set at 2.8, so we jumped up a little bit, but then it came back down. So everything was good. This hits 4% just barely, but we are within spec, so everything is good to go. It also should be noted that the calibrated bread tie is holding up very well, and I've not had the high range is not slipping, which is what the important part is, so the frequency's pretty spot on. This does take a little bit longer than I expected to warm up, so when I turned it on, I thought it had slipped, but it ended up coming down and being right where it needed to be after an appropriate warm-up. Thanks for stopping by the lab, taking a look at the SG504. This one gave me some trouble. It wanted to argue a little bit, but it's all set. Hopefully we don't have any problems given what we have found out, but it's ready to go to help me work on that scope frame. So thanks for joining, and I will catch everybody in the next video.